Hi everyone. In the previous class we learned about the real numbers. The continuation for today's. And in the previous class we learned about natural numbers, whole numbers, integers and the rational numbers. Today we will go for the rational numbers and its properties.
Decimal representation of rational numbers. Here we can represent this one in two forms. That is, one is a terminating decimal and one is a repeating decimal. Once I will take example for the terminating decimal. See, here I am taking 1 by 2. If I do division, it won't go. So keep the decimal and 0. 2 5s are 10. So here the 1 by 2 equals to 0.5. Here repeating decimal. I am taking here the one example 1 by 3. It won't go. So I am keeping the decimal. So then 0. Here 3 is a 9. 10 minus 9 is a 1. You can keep a 0. 3 is a 9. 10 minus 9 is a 1. 3 is a 9. 1. I think you can observe here very clearly. 10 minus 9 is a 1. Once again 10 minus 9 is a 1. Means the 1 is coming continuously. And here in a quotient 0.333 it's a continue. So 1 by 3 equals to 0.333. We can represent this one 0.3 bar. Here ending, when we are doing here the division, here we are getting a remainder as a 0. So then that decimal is called as a terminating decimal. While doing here, we are not getting a remainder as a 0. It is coming a same number. So that's why we call this one as a repeating decimal. Terminating decimal. If after a finite number of the steps in the division process, when no remainder is left, then we call the quotient as a terminating decimal. So I'll take a few examples. Here I am taking 11 by 2. So 2. So 2 here 11. So 2 5s 10. So 1 minus 0 1, 1 minus 1 0. So keep here the decimal, and when we keep here the decimal, then we can keep here the 0. So 2 5s 10. See, 11 by 2 equal to 5.5. $15 by 5 I am taking. 5 3s 15. Here also we can say that 15 by 5 equal to 3. Otherwise 3.0 also we can keep. More one example I will take. $27 by 5. 5 5s 25. 7 minus 5 is 2. Keep the decimal point because that remainder is this number is less than this number, so you can keep here the 0. 5 fours so 27 by 5 equal to 5.4. So according to the definition, the terminating decimal, if after a finite number of the steps in the division process, when no remainder is left, means here we are getting the 0, here also we got the 0, then we call the quotient means this one, here this one, as a terminating decimal. Repeating decimal. A decimal in which a digit or set of the digits repeat continuously is called a repeating or recurring or circulating or periodic decimal. We'll take one example. So here I taken the 5 by 3. So 3 table I am using. 3 ones 3. 5 minus 3 is a 2. See, here the remainder is less than the divisor. So then it is not possible to divide directly. So then I am taking here the decimal point. Then I can keep here the 0. 3 6 18. So once again 2 3 6 once again 2 3 6 once again 2 3 6 Here 5 by 3 equals to 1.666. It's continuously 1.6 bar we can say. According to the definition, see, after the decimal place the digits are recurring, means repeating continuously. So then we can say this decimal as a repeating decimal, otherwise recurring decimal, circulating decimal, periodic decimal also we can call. I'll take one more example. (17 by 6). So 6 2s 12. So 17 minus 2 is 5. See here the 5 and here the 6. So it is not possible to divide. So then 6 is a greater number and 5 is a smaller number. So I am keeping here the decimal 0. 6 8s 48. 50 minus 48 is a 2, and here we can once again keep the 0. 6 3s 18. See, 20 minus 8 is 2 and 0. 6 3s 18. 20 minus 8 is a 2, so 0. 6 3s 18. It's a go on. So continuation. So 17 by 6 equals to 2.8333. It's continued. So we can write 2.8, only this 3, means here the digit 3 is a recurring, means it's a repeating. So that's why 2.8 3 bar. Bar is for only 3, because the digit which is recurring, for that only we can use. I am taking here the 9 by 11. For this, with 11 table, I am going to divide 9. See, 11 zeros 0, the 9 came, and decimal here you can keep 0. 11 eights 88. So 90 minus 88 is a 2, so it won't go. You can keep the 0. 11 ones 11. 20 minus 11 is a 9. We can keep 0. 11 eights 88. Here once again 2 and 0, 11 ones 11, 9, 0, 11 eights 11, ones 11. Once again we are getting here the 9. Here the 2 digits are the repeating. So we can write as like 9 by 11, that is equals to 0.818181. It's a continued. Then we can write in a short form, that is 81 means here the 2 digits are the repeating. So that's why I am keeping a bar for the 2 digits, 8 and 1 also. So we can read this one as a 0.81 bar. Notation of a repeating decimal numbers. In a repeating decimal, if number of the digits are repeated, then a dot is put on each of the first and the last repeating digits, or a bar is placed on the entire period of the repeating digits. Here I'll take one example. One by 3, there's a 0.33. We can represent this one as like 0.3 because here only one digit is repeating. So then I am keeping 3 upside dot, or 0.33 bar means the bar under digit is repeating continuously. I'll take one more example. There's a 1 by 11. There's a 0.090909 continue. Here that first digit is a 0 and the last digit is a 9. Means these 2 digits are repeating continuously. So I can write this one as like 0.0. See, 0 is repeating now, so that's why I kept it's the first digit. So I kept a dot on that. And last digit is a 9 because these 2 digits are only repeating. So I am keeping here the dot, or 0.09 bar. So I'll take one more example. 22 by 7, that is equals to 3.142857 as like continue. Here see, first digit is a 1, decimal afterwards first digit is a 1, and here the last digit is a 7 because up to here this all digits are repeating continuously. So then how I can write now 3.142857. See, 1 upside dot and 7 upside dot means this is a starting digit, it's a last digit, or 3.142857 the whole bar means this all the digits are repeating continuously. From the observation we can conclude as like a fraction p by q is a terminating decimal only when prime factors of the q are 2 or 5. Otherwise p by q is a non-terminating decimal. Once we will check it here 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by 6, 1 by 7, 1 by 8, 1 by 9, 1 by 10. By seeing only we can say it's a terminating or the non-terminating. 1 by 2, see, according to the definition 2 or 5. See, downside that q is a 2, so terminating decimal. 1 by 3. See the Q is a 3. It is not satisfying, so it is a non-terminating decimal. 1 by 4. See 4 I can write a 2 into 2 means a factor of the 2 into 2. So then it's a terminating decimal. See here it is a 5. So in the definition itself they given that is a 5. So then it is a terminating decimal. 1 by 6. 6 I can write as like 2 into 3. 2 is there, okay, but 3, when the 3 came, then immediately we can write that it is a non-terminating decimal. 7 we can say directly this is a non-terminating. 8, see I can write 8 2 into 2 into 2. So all the denominator 8 I can write in a factor of the 2 into 2 into 2. So then I can say this one is a terminating decimal. 9 3 into 3, but it is not satisfying, so then it's a non-terminating decimal. 10, see 10 I can write 2 into 5 means 2 5s are 10. So then definition here 2 5, so then it is a terminating decimal. Means by seeing the denominator we can decide that number is a terminating one or the non-terminating one. Density property of rational numbers. Between any two rational numbers there exists a infinite number of rational numbers. Okay, once we will recapitulate our previous knowledge. If we take whole numbers start from the 0 onwards, and 1 2 3 4 as like go on up to infinite. If we take see in between of the 0 and 2 1 is there, in between of the 2 and 4 3 is there, as like we can say. If we take integers, integers 0 1 2 this side minus 1 minus 2. Suppose if we take in between of the minus 1 and 1 positive 1 0 exists, in between of the 0 and 2 plus 1 is there, in between of the 0 and the minus 2 minus 1 is there. Now we will come for the rational numbers. I am taking here the 0 and here the 1. In between of the 0 and 1 any number is exists. If it exists, how we can find out? See here, if I think this is A, this is a B, the in between number I needed, so that is A plus B divided by 2, then I will get a in between number. Now here it is a 0 plus 1 divided by 2, that is equals to 1 by 2, means it will come here 1 by 2. In between of the, I am taking this 1 by 2 as a C. In between of these two, any number is exist or not, once we will check it. Here this is A plus C divided by 2, that is 0 plus 1 by 2 divided by 2. This we can write 1 by 2 by 2. So I can write this 1 by 2 into 1 by 2, that is 1 by 4. Means in between of the 0 and 1 by 2, here once again 1 by 4 is there. If I take once again this and this, I am taking this one as a D. So A plus D divided by 2, that is 0 plus 1 by 4 divided by 2, that is 1 by 4 by 2. This 2 I can write by divided by 1. So 1 by 4, if I bring this 2 by 1 upside, then it is 1 by 2. It will become 1 by 8. Means in between of the 0 and 1 by 4, here 1 by 8 exists. As like wherever you take, there in between number will be exist. So that's why we can say as like in between any two rational numbers there exist infinite number of rational numbers. I think now by seeing this you can understood, I think got an idea about this topic.